All right, I think we'll get started. Thanks everybody for coming. Today, Alex and I will be talking to you about precision time protocol on StarlingX. So I'm Matt Peters from the StarlingX community, and specifically a software architect at Wind River.
And I'm Alex Kozyrev. I'm working on the StarlingX platform and mostly covering the performance features of the StarlingX platform.
And for StarlingX specifically, I am the networking tech lead, so I help with defining some of the technical features for the networking side of StarlingX, and helping out today with the presentation for PTP. So how many people are familiar with StarlingX? Or I know you've heard of it now by all the keynotes and stuff, but how many people actually know what StarlingX is? All right, so today I'll take you through a bit of an overview just to set the context. I won't go through all the material, obviously, just enough to set the stage for some of the stuff that Alex is going to talk about and make sure that there's continuity between some of the software components that he's talking about and some of the components within StarlingX itself. I'll do a little bit of an overview of the PTP operation and some of the use cases that we're seeing PTP deployed in. And then I'll hand it off to Alex to go through the StarlingX architecture and software, followed by a demo. So just a few factors that underpin StarlingX. So these are promoted on the most edge sort of use cases, but I wanted to go through sort of what these mean for StarlingX specifically, and just how we can adapt to some of these things going forward and stuff that we've already done to make sure that we address some of these factors. So on the reliability side, for StarlingX, this really is about fault detection and recovery, and that's an automated recovery, so to reduce and minimize the downtime. On the scalability side, what we're looking at is not just scaling out to thousands of nodes, but we're also looking at the aspects of scaling down to something that's much smaller. So we need to be able to handle very small footprint, all-in-one type nodes. So that's something that we do as part of StarlingX, and making sure that we have the smallest footprint possible, but then still have the flexibility to scale up to something that meets the use cases that we're seeing in the edge. And as you've seen in many presentations, edge is broad. It's not defined, just in one specific band. It goes from the far edge all the way up to the provider side. So it spans many facets. On the latency side, so this is important definitely for the edge use cases, what's driving most of the edge scenarios. But for StarlingX, what this really means is that we've taken the extra time to go through and make sure things are deterministic, that things are tunable, and to make sure that we've done the due diligence to make sure that we get some guaranteed latency within our system. So not just saying, this is the minimum requirement we have to work to, we actually measure that and make sure that we can get to that point. On the edge security side, so we know that we can't always deploy into a physically secure environment. So a lot of the work that we do is to be able to make sure that we can look at tampering, what's the attack surfaces for our system, just really looking at how people can get into the system and making sure that we have the protections in place so that doesn't happen, and the audit trail to make sure that if something does happen, that the information can be retrieved later for any forensic analysis. And then finally on the lifecycle management is making sure that we have a deployable solution. So StarlingX itself, as you'll see in some of the software components, is a fully deployed solution, a deployable solution of Kubernetes and OpenStack. So it's making sure that we have both the deployment aspects covered off and the operations for a full system management. So diving into some of the virtualization platform, and actually this really should be expanded to the containerized platform. We're really looking at the different software components and the lineup that make up StarlingX. So it is based on a number of open source projects, but we bring those together into a consistent and deployable solution. And that particular solution is tailored and tuned for the edge use case. So we're not looking to expand into large data center. This is really just about having either a large or a really small edge deployment. So if you look at the software lineup, at the very bottom of it, we call out Linux pretty generically there. Today we deploy on CentOS. We are looking at a multi-OS work to be able to deploy this on different platforms. But really, it's a curated distribution of CentOS. And again, it's tuned specifically for the edge use case. Above that, we have Kubernetes. and its supporting components. So we have a number of things not necessarily called out here. It's hard to list them all, but I still have a slide that you can read there. But really, we are a cloud native platform first. So we deploy out of the initial deployment is a Kubernetes master node and the rest of the stack. So with the initial single node install, you start off with that Kubernetes platform, and then from there we build out either adding additional nodes to the system to be able to scale out for additional resources, or you actually have applications that you deploy, and one of those applications is OpenStack. So we deploy a containerized version of that OpenStack and therefore get the full management and orchestration of those virtualized workflows. And for us, we have aligned on using Ceph as our persistent storage. So we do that both for Kubernetes and for OpenStack. So the persistent volumes and any of the OpenStack solutions like Lance or Cinder all use the Ceph cluster. And then we have the flexibility to be able to use external storage or other storage solutions as well. But the default deployment is a Ceph cluster that's managed and deployed using StarlingX. So then we come into the software component specific to StarlingX, which is the middle row there, which we call the flock of services. And what this is really tailored to is the infrastructure management. So we have the infrastructure orchestration on the right-hand side that interacts with a lot of these services. So each individual function has a standalone operation. And I'll go through that at a high level. But together, we also have the infrastructure orchestration that ties it all together to make sure that as you do your operations, you can have the interaction between the different services and they coordinate their operations. So on the configuration management side, this deals with installation and commissioning, hardware discovery, and node configuration. So this is something that has been in development for some time, and it's sort of evolved to covering off more than just the hardware inventory, but it deals with our software management side of things. So it deals with the host configuration after the initial deployment as well. So if we have configuration to push out to the system, it deals with applying that to the running system as well. The host management side deals with the lifecycle management. So this is the interaction with the physical servers, the monitoring of those physical servers, fault detection, reporting, recovery, and failure. So it's pretty broad, but really what it comes down to is we're monitoring the physical resources for any anomalies, looking at the capabilities for those as well to figure out what their monitoring capabilities are. So if it's got a BMC, then we'll be able to configure that to do the power management and also get specific sensors out of it to be able to look at power consumption, heat, and that kind of thing. On the service management side, this deals with our platform services. So we have a fully monitored system. So every process in the system that runs on the bare metal is monitored. So whether it's monitoring the life cycle of that process or it's doing health checks with that system, it's going through and doing the insurance that the service is up and running and providing its function. And if it's not doing it, it'll service, then it'll do a failure recovery to be able to recover that particular service. So whether it's a process restart or an entire switch of activity to try and move to a different controller if there's, if it's a redundant service. So it'll go through and make sure that it can handle that scenario. And then there's a set of software components that work in concert together. So we have the software management piece, and this deals with software updates, both to the kernel and for any of the other components. So if there's an upversion in one of the RPMs, it'll take care of applying that update to the system across the entire system, the entire cluster, and also to any of the individual host OS as well. So if there's a kernel update, it'll actually go through and do the interaction with the infrastructure orchestration to apply that update to the entire cluster rolling through and moving workloads off, making sure that the system stays up. And then finally, the fault management. So this is dealing with the reporting and alerting to the customer. So being able to persist some of these events or distribute these events to operations. So if you have SNMP feeds or you want to come in through the API, this sends out alerts and some of the logging events to that operations. And finally, just as a look at some of our actual deployment capabilities. So we have a single server which can run all the functions of compute, control, and storage. So this is what I was talking about, being able to scale down to an individual node. So this is obviously not an HA deployment. This is other than just the localized service monitoring. But if you do need the HA, then you go to the dual server mode, which is the 2 all-in-one nodes that are set up in a paired configuration. And then we expand to a multi-server configuration, which is your typical OpenStack deployment model that you see, or a Kubernetes model where you have master and worker or compute functions that are spread out over multiple servers. And then we take the same multi-node deployment, whether it's a single node or a multi-node, and then we also support this in a distributed cloud fashion. So having a central controller, being able to orchestrate a number of edge clouds as well. I'm not going to go into a ton of detail there because I think that's several talks on its own. So we'll just leave it at that. The only reason I wanted to bring it up is because it is something that we cover off in the PTP side of things about distributing out the time source and the configuration for that. So let's dive into PTP, which is one of the main reasons why we're here to talk about. So I want to start us off with a quote, which I think sums it up pretty nicely, which is the fact that PTP is really targeting a specific use case that's not normally addressed by NTP. And there's lots of advancements that is being done in NTP to make it more accurate and doing other things, but PTP has really sort of evolved to what we're seeing as the main primary clocking source for the edge. And that's really just from its legacy as well. I mean, it's already present, whether it's got existing deployments with the GPS signal coming right into the device directly, or if it's something that they've already got PTP deployed and they're just looking to move that existing physical infrastructure over to a different platform. So the things that are driving PTP to be the highly adopted is some of these. So I'm not going to call them all out, but I think the biggest thing to highlight is just the fact that it does have the sub-microsecond capabilities that the edge is looking for. So if you get into some of the more advanced LTE or the 5G, they're looking for sub-microsecond accuracy in their latency. And the small cell configurations where they're doing the handoffs to the different sites, that they need to be able to have that accuracy so that the handoff is smooth and that transition happens. And if you look at some of the other capabilities that really makes PTP a good thing to deploy, is that it can be done on commodity hardware. So you do need the hardware support from the NIC or the switches, but you're not looking at customized or specific deployed hardware to be able to bring that clock source out to your network. So you still have to have a particular clock source that is coming from like a GPS signal that is highly accurate, but you can, in a cheap way, distribute that out to all your nodes in your cluster just by chaining that throughout the system. And I captured the history here just because I wanted to call out some of the stuff that's happening for some of the future versions of PTP, and I think it's important just to highlight the fact that they are looking at things that are even like sub-nanosecond accuracy. This is what they're deploying at CERN. So a lot of the things that they're doing in the community to advance PTP, they're actually bringing back into the future specs of PTP. So sub-microsecond seems hard to obtain, but even sub-nanosecond seems even harder, but it is capable of doing it, and even with some of the existing protocol. So the standard deployment for PTP is typically this setup where you have a hierarchy. So you'll bring your clock source in from a top highly accurate clock source. The algorithm itself will detect the best clock source within the network. So from a customer administration perspective, they don't have to necessarily pick the best clock source. So if there's something that happen, if they have redundant configurations where they have two GPS signals coming in and they have it deployed with redundant clock signals, it can automatically resolve sort of the best clock at that time. So if there's any faults in that signal, they can adjust accordingly. And it also handles isolation. So if that clock source goes away, the rest of the network can still operate independently without that additional clock source and resync once it becomes available again. And then finally, I think the biggest thing is that everything is done automatically as far as the state negotiations. So the master-slave negotiation that happens is all automatic. And from an operations perspective, that makes it much easier to manage. You don't have to deal with reconfigurations in your network. You can deploy new nodes, and it'll take care of the reconfiguration. So where we're seeing the most adoption for PTP is across a broad spectrum of industries. And there's a few out there that you'll hear for TSN because it's becoming more popular and how they're leveraging PTP within those specs itself, coming up with specific profiles for TSN. But we're seeing profiles across the board for all the different industries. And they're even taking a lot of those industry-specific profiles and pulling them into the next version of PTP. So we're taking sort of the best of breed for all these modifications that the industry has done and pulling it back into the standard where it makes sense, and then leaving the individual profiles to any of the specific industries. So with that, I'm going to hand it over to Alex to go through what this deployment looks like on StarlingX.
Yeah. Okay, so I'm going to talk about how did we implement the actual PTP on the StarlingX platform. And let me go back to this PTP architecture diagram first. And I will highlight the StarlingX nodes roles in this architecture deployment. Basically, as Matt mentioned, to get the best results from the PTP, you need to have some kind of grandmaster clock where it's GPS backed and it gets the accurate timestamp from the GPS. And after that, you can propagate this accurate timestamping to our StarlingX controller, so-called controller nodes, where all the components are managed. And one of the controller nodes will get the time stars and propagate it from the OEM network, where your grandmaster clock is resided, to the management network, where all the compute nodes are present in the StarlingX deployment. Basically, the idea of PTP is to get the accurate timestamping between your workloads that were running on the compute nodes. So PTP allows you to synchronize different workloads running on them with very high precision. And it doesn't matter if you are running them inside your Kubernetes container or inside a virtual machine. But if you have no grandmaster clock configured for some reason in your deployment, we can go to the simplified PTP deployment architecture, where one of the controller nodes takes the responsibility of grandmaster clock and will just send its timestamp to all the compute and controller nodes. So basically, all is done automatically, and it's based on the PTP best master clock selection algorithm, and it requires a little intervention from the user point of view. And how we did the PTP implementation as an open source project, we took another open source project into our platform and integrate Linux PTP binary. So it's a pretty standard implementation of the 5088 standard, and it's well maintained, and it has a dual strategies in tackling the PTP implementation. Basically, it implements the latest standard of the PTP protocol, and also it leverages from the latest API provided by Linux kernel to simplify and achieve the best high performance quality of the time synchronization between the PTP clocks and the Linux system clocks. There are actually a couple of configurations you need to be aware of. So basically, Linux PTP consists of two different binaries. One is PTP for Linux, which is actually PTP implementation, and it allows you to transmit PTP packets over the network. It allows you to participate in the BMC protocol to elect the best clock source in your network, and it communicates over the UDP over IP or raw Ethernet. Also, there is such a thing like a delay mechanism. Basically, it says how you actually calculate the network delay between your controller and compute nodes, for example. There are two different options. One of them is end-to-end, and which means that you need to have both controller and compute nodes communicate via PTP protocol to measure the delay between them, network delay. And it's a standard and common way to do this, but it does not take into account all the network topology, how many switches do you have between your compute and controller nodes and so on. So it's good enough, but if you want to achieve the better quality of the time synchronization, I would recommend to go with peer-to-peer communication, because it measures the delay between every single segment in your network, between every single node and every single switch in your network. But in order to do that, you, of course, need to have PTP-aware switch between your nodes, and you have to configure it as well. And the last configuration point that also affects the accuracy of the PTP is it hardware or software timestamping? Software timestamping means that you get your timestamp from the application itself, from the PTP for Linux binary. And it's not good enough because you need to propagate it through the network stack, through the network drivers, through the Linux OS, and send it out to the network. And that's why most of the network cards right now support the hardware timestamping. So basically, you take your timestamp during the packet sending out to the network, bypassing all the OS latencies and so on. And the second binary is PHC2sys, and it acts like an intermediate between the hardware PTP clock and the Linux system clock. Basically, it just synchronizes these two clocks on your system. And to hide all the complexities of this stuff, this is the slide that represents you with the PTP configuration in StarlingX platform. Basically, there is one single command you need to run on your controller node, and that's it. You need to choose your mode, software or hardware, your transport protocol, and delay mechanism you would like to use in your network, and that's it. And after that, StarlingX configuration manager takes all the parameters and distributes them across all the controller and compute nodes, applies them, and you are ready to go. Basically, that's how you deploy your PTP configuration in StarlingX. Nothing is required other than that. And to make it even easier, we have a StarlingX GUI interface. It's Horizon web page, which allows you to do a couple of clicks, select all the needed information, enable PTP, and that's it. Everything is done automatically after that. And moreover, we have a so-called distributed cloud configuration when we have one central data cloud, central data center, StarlingX data center, which acts as the shared configuration manager for multiple edge sites that can be distributed geographically around all the globe. And the beauty of this distributed cloud that central data center is responsible for taking all the shared configuration. You can go ahead and configure PTP on the centralized data center, and all the settings are going to be propagated to the edge sites automatically for you. Basically, if you have a distributed cloud in one building and another building, you just need to go to one web page, select I would like to have the PTP on all of my edge sites, and that's it. Everything is done automatically as well. Okay, so basically after that, you have your PTP protocol running and set up in the StarlingX nodes, but the idea is not to have the same timestamps on your controller nodes, on the compute nodes, because you don't care about that. What you care is about synchronizing your workloads. So you would like your application distributed geographically to run at the same time with the high precision. So basically, if you have a workload that is running inside the container, it's automatically done for you, because containers use the Linux system clock, and they take timestamps from them, and it's already good enough. But what happens if you have the virtual machine? And good news that there is a KVM virtual PTP driver that allows you to get the timestamp from the underlying host hardware and propagate it into the virtualized environment. And it's simple as well, because you just need to point your time synchronization program inside the virtual machine to point it to the virtual PTP device inside the virtual machine, and that's it. you can get almost the same timestamp. The accuracy is very high there as well. And on top of that, after you did your deployment, PTP deployment, you of course need to understand if it's working fine, if it satisfies your requirements, and if it's fails, you need to know right away about that. So in StarlingX, we have a monitoring capabilities that constantly collects all the timestamps, all the offset between the controller and compute nodes, and stores in the database. Basically, you can, after that, grab all this information and see how it was behaving during your deployment. And also, we automatically notify user about any unacceptable skew between the compute and controller node. So for example, if for some reason your PTP setup is not good enough and the difference between the time on the controller and on the compute nodes are more than 1 millisecond, we immediately notify user about this error condition. And also we check that every single network Ethernet card on your compute nodes are compliant with the PTP and can support the hardware timestamping, and if not, then we notify the user about the inconsistencies with the compute node configurations. And here is the most important slide I have today. So basically what I did the latency measurement in different various scenarios, and what I actually measured, it was the delay between the controller host and compute host as a first step, then between the hardware clock on the compute host and the Linux system clock as the second step, plus the difference, the offset between the compute host time and the virtual machine clock. So basically I summarized all these three offsets, and this is how it looks like. Basically, even with the simple configuration standards in StarlingX configuration, when you just enable PTP and that's it, you can have a pretty decent average offset between your virtual machine. So it's about 100 nanoseconds only. But the problem is we can have occasional spikes that can negatively affect your performance in your virtual machines, and it can be up to 1 microsecond, as you can see on this graphic. And what can I do to improve the situation? Basically, there are two main factors that affect the performance of the PTP. One of them is the network configuration, and the second one is the underlying platform latencies. For example, Linux OS scheduler is not fast enough to provide you with the time source, and virtual machine itself is not scheduled fast enough. So to tackle with the first problem, with the network configuration, all you need to do is to invest into the PTP-aware network switches and configure them as the PTP transparent clock or boundary clock. After that, you will reduce significantly the offset between the controller and the compute hosts. As you can see on the graphic, it's slightly better in terms of the average latencies. It's less than 100 nanoseconds. And the spikes are almost gone. So it's about 350 nanoseconds right now. But if you would like to improve it further, I would recommend to set up the low latency StarlingX compute nodes. Basically, low latency StarlingX profile is the real-time operating system, real-time OS, real-time Linux patch, plus somehow optimization in the performance. Plus, you get the VM pinning to not interfere with the OS scheduler on the VM-only cores. And having both network switches as the transparent PTP clock and the low latency profile, we can reduce the latency down to the 150 nanoseconds. And the average is about 50 nanoseconds, which is great. And basically, that's all I have today. And I would like to show you the actual demo or how you configure and set up the PTP functionality and how to check the behavior of the PTP on your platform. And that's it. Let me start the video there. Okay, so let me start with the seamless cluster orchestration. So when you go and log in into StarlingX portal, you can have the simplified single pane glass view over all the compute and hardware nodes on your deployment. Basically, you go to the host inventory, and you can see in this case we have a 2 controllers node, 2 storage nodes, and 4 compute nodes. And to make it PTP adjustable, so we go to the PTP system configuration platform and check the edit PTP, check the enabled, and click save. Basically, that's all needed for the PTP deployment. One thing I need to mention that we cannot have both NTP and PTP because both of them will attempt to modify your system clock, and it's not allowed in our setup. So before you enable PTP, you need to go and disable NTP first and save it. And then go back to the PTP page and select all the needed configuration details, so such as hardware or software timestamping, which delay mechanism, and which the network transport you are going to use. Yeah, after it, are you happy with this configuration? You just click OK, and that's it. After you created this PTP profile, it's automatically applied to the whole compute and controller and storage nodes. But one thing you need to perform is that you can see that configuration is out of date alarm is raised on the all the platforms because you cannot adjust the system time on the fly. We do not allow it because it might affect negatively your workloads already running on the compute nodes. That's why we require you to lock and lock, perform the lock and lock operation. Basically, it takes your compute node out of the operation, move all your workloads to another compute host, and perform the reboot to apply the PTP configuration and to set up the initial timestamp because we do not allow the high frequent time jumps on your system, which can affect negatively your workloads. And after all the nodes are put up, you are good to go. Yeah, here is the simple page that shows that everything is in sync right now. And we can go to the system configuration and check that NTP is disabled and PTP is enabled. Okay, so now I'm going to check how it operates actually. So I'm going to log in into compute node and check if PTP is actually running there and how it behaves. So basically, if you go to the compute node and grab for the PTP for Linux binary, we show you all the parameters. The beauty of that we automatically generate the PTP for Linux configuration based on the information you provided in the web interface. And to check the performance of the PTP for Linux, for example, you can go ahead and grab the system log file, and it will show you all the offsets between the compute node and the controller nodes. And also you can check the second binary to see what is the offset between the Linux system clock and the PTP hardware clock. This is the information you can grab and feed into your external validation tool to see how it behaves. And another tool is available on the platform is called PMC. It allows you to check the PTP hierarchy. It allows you to check who is the grandmaster in your network and what is the actual performance, actual offset between the grandmaster and the slave clocks. And the next video will show you how to check that the virtual machine is synchronized to your compute host. So basically on this virtual machine, I go to the chrony.conf file and show that the PTP hardware clock is no reference clock for the chrony daemon. And if you type the watch command for the chronic, it will show you how it operates actually. Yeah, as you can see, the chrony daemon inside the virtual machine use the PTP hardware clock. And here is the offset between the compute host and the virtual machine itself. So it's about 50 nanoseconds right now, and it fluctuates. That's all pretty simple for user to do. And yeah, the last part of the video shows you, I exported all the measurement. I let it run for the extended period of time. So I remember running it over the weekend on my platform. And I collected all the offset information between the compute host and the controller host and captured it into the Grafana tool. And here you can see that the actual PTP performance was pretty good. It was about 50 nanoseconds in average. And there were some occasional spikes, but they do not exceed the 200 nanoseconds, which is pretty amazing for this simple setup. So basically, yeah, PTP on StarlingX allows you to achieve the sub-microsecond separation, synchronization between your workload operations. And that's it.
All right. Thanks, everybody. Is there any questions? Go ahead.
So I guess the synchronization happens over the management level.
Between the compute and the controller node, right?
So what if the controller itself gets the timer from, say, some other source? Who will get this other source? So the controller will be a transparent bound in that instance, right?
Well,
because this is just, I mean, you have to look at the entire chain of time, from the grandmaster, wherever it changes. You can't make any assumptions. Controller is. And the controller itself may derive its timing from somewhere upstream.
yeah, that's right. If you have a grandmaster clock, external source of the precise time stamping for your platform, we get the timestamp from this external time source on the controller side. And the controller itself is the slave for this grandmaster external source. But it needs to propagate this exact timestamp that you get from the grandmaster to the other nodes. That's why we have controller acts as the boundary clock, so-called boundary clock in terms of. Controller is the boundary clock. It takes the precise timestamp from the grandmaster over the OEM and management OEM network and propagates this timestamp to all the controller nodes, compute nodes over the management network.
So how does this compare to PTP in terms of packets?
Accuracy is much higher here because of the functionality of the PTP. For example, it takes the timestamp from the network interface card directly, which reduces the delay latency, and NTP doesn't care about the delays. So PTP aware about your network topology, and it calculates the delay, the network delay between the two different hosts, and takes them into account. So whenever you get the timestamp from the grandmaster, you know that this was the exact timestamp on the grandmaster, plus you know the latency in your network. You calculate the latency in your network and takes into account as well. So basically you can compensate for all the inefficiencies across your network topology in case of PTP, which is not possible with the NTP.
And you mentioned that there's no special link that's needed even though there's some acceleration, even though, did I hear you say that we need a special NIC for this?
For now, most modern NIC support the PTP hardware implementation, basically. So I don't think you will ever see the network interface card that do not support it on the carrier-grade network servers.
Yeah, it's usually harder the other way around. It's hard to find one that doesn't support it. So.
Is there any difference in performance when you run on UDP versus Ethernet?
No, I didn't see any difference in that case. The only difference is in the performance is about is it hardware or software timestamping and the delay mechanism you're applying. But in terms of the packet transmission, it doesn't matter. So you can send it through the UDP or over the net.
And what is like the resource needed to keep PTP running all the time? How many CPUs and what's the overhead consumed?
Well, I didn't take any measurement about the overhead, but it was pretty low. I didn't see any adverse effect of doing that.
It's actually one of the key features of PTP that it does work at very low resources, both memory and CPU. It can be deployed on a microcontroller, it can be deployed on a compute host, so it's one of the features of why.
But if you keep increasing the frequency of the timestamp in order to ensure nanosecond accuracy, then it is going to take a lot of resources.
Well, the PTP protocol is smart enough. He knows about all the network topology already, so it doesn't need to send it frequently. So basically it takes, I believe it sends by default one packet in 1 second only. You can increase this frequency, of course, but...
It's just how much drift you can tolerate in your time source.
You could send it 128 times a second, and that would walk around the whole network potentially.
Yes, yeah.
Yeah, correct.
There's an additional question here.
So, you talked about mix. What about virtual machines? Like, I believe the hypercore that you mentioned for virtual PTP, it's present in your kernel. So, what do you do in that case? Do you go back to hypercore?
Well, it's up to you how do you configure your virtual machine. So if you have a virtual machine that supports the PTP hardware clock, you can do it. Basically, a KVM has this virtual PTP driver, and this is our main source of the virtual machines. I don't know about. Yeah, Zen virtual machine has its own, so you can configure the Zen virtual machine to use the PTP hardware clock as well.
But StarlingX uses QEMU today.
Yeah.
All right, I think that's it. Thanks everyone for coming.